Hi everyone, and thank you all for joining us today for the 7th in our series of webinars for 2017, which discusses LimitState software. My name is Tom Pritchard. I'll be introducing you to our main speaker shortly and also rounding up at the end. Today's webinar concerns the modelling of retaining walls using LimitState GEO, and it will provide you with an overview of how you can use the software to undertake geotechnical stability analysis to rapidly determine the critical failure mechanism and also the margin of safety for a range of geotechnical problems, mainly involving structures such as gravity walls, cantilever walls, anchored or prop sheet pile walls. The webinar will run for around 45 minutes in total, and we will include some time at the end for answering any questions that you may have. You can post these at any time using the question functionality that is present in the webinar interface on your screens. We do have a mixed audience today from right around the world. Some of you will be quite familiar with LimitState GEO and some of you will be relatively new to it. We will try to answer as many of your questions as we can in the time available, but given the number of people that are attending today, it might not actually be possible to get around to everybody's. So apologies if we are unable to get around to yours, but we will always ensure that we reply to everybody via email in the days following the presentation. So without further delay, our speaker today is Dr. Colin Smith, who is the LimitState GEO Product Manager, and I'll now pass you over to him.
Okay, thank you, Tom. So good afternoon or good morning, depending on which time zone you're joining us from. As Tom has mentioned today, my aim is to show you how LimitState GEO can be used to solve retaining wall problems, how it differs from other methods, and how to model a number of specific scenarios. So to this end, I'll be using a mix of slides and software to illustrate the key points. As it's a problem-specific webinar, I'm going to focus on how the software can be used to solve retaining wall problems, so might therefore skip over some of the details of how to use the software, but hopefully the process should be clear. So that's a brief outline of what we're going to cover today. A little introduction to retaining wall analysis, look at geotechnical analysis software, and then we're going to look at gabion gravity walls and cantilever anchored sheet pile walls. So I think it's useful first to give some context to the software and to the company LimitState. So the University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And the company LimitState was spun out from the university in 2006 with the aim of making this research available to industry, providing easy-to-use, powerful software tools that are well validated and supported. The company has 3 civil engineering products at present: LimitState Ring, LimitState GEO, and LimitState Slab, and several more in the pipeline. And these are used by consultants and contractors, large and small, in over 30 countries worldwide. This is just a list of the top of our page of clients that use our software. Now, in terms of LimitState GEO, this slide illustrates a range of capability of the software. It's fully general software, able to determine the collapse state for any problem geometry, and it's able to model slopes, retaining walls, structural elements, or soil reinforcement, or any combination of these as shown by some of these examples. So our aim today is to focus on the retaining wall analysis, examples of which are shown in the top right and bottom left of this slide. Now, before we get on to how the software performs that type of analysis, it's useful just to recap on some basic theory. So if we examine the standard textbooks or design codes, we can see a broad consensus on the general principles of retaining wall analysis, which are adapted for specific scenarios. And quite often a limit equilibrium approach is used. You might use either a Rankine earth pressure or Coulomb wedge approach. So if Rankine earth pressure, we're predicting the pressures acting on the back of the wall. So it's very useful for determining pressure distributions, but it's a little tricky to account for variable backfill geometry or non-uniform surface surcharges, and it doesn't give us the extent of the mechanism, so we have to use other sort of indicative methods to give us a feel for those. On the other hand, a Coulomb wedge analysis is quite capable of handling variable backfill geometry and non-uniform surface surcharge, does show the extent of the mechanism, but it's difficult to use for determining pressure distributions on the wall, and if we only use one wedge, we may not get a very accurate answer. Now, what LimitState GEO does is essentially a Coulomb wedge analysis, but instead of working with one wedge, we basically work with thousands and thousands of wedges to give us a very accurate answer that is able to provide a solution to any problem type that we care to look at. So this shows a few examples of the types of problems that we can see: key walls, gabion walls, cantilever stem walls, and also sheet pile walls. And the method, because we can use thousands of wedges, it's able to give us pressure distributions and moment distributions on structures also. So how does that particular method work in detail, and how does it relate to other geotechnical software? So just to give you a little bit of context there, typical software that you might find available, on the one hand, in the top left corner we have what we might call traditional methods. So these are essentially software that automates a conventional hand calculation type approach, such as method of slices for slopes, or adapted Rankine methods for earth pressures on retaining walls. On the bottom right, we've got the fully nonlinear finite elements that can model any problem scenario in great detail, but requires more time and skill to use, whereas in the top left we've got solutions which are nice and quick and easy to use and fairly easy to get your head around. But we think there's a gap in the middle here, and that's really what we call rigid plastic analysis, of which LimitState GEO is one particular example. And what this does is it takes the simplicity of the top left approach, in that we only need to get parameters, cohesion, friction, and unit weight for the problem, but it allows us the flexibility, the finite element approach, that we can model any problem geometry and range of soil properties and loading regimes. And this kind of approach can be applied not only to geotechnics, but as in our other products, to masonry arch bridges and in slab analysis. So how does it work? Well, the key enabling technology is called discontinuity layout optimization. It's a rapid and direct means of analyzing the collapsed state, and was the outcome of a 5-year funded research project at the University of Sheffield. The key method was published in the Proceedings of the Royal Society in 2007, and there have been various other publications since then. But it's quite straightforward to explain in simple terms how it actually works. So here we have a block of soil with fixed boundaries to the left and to the base, with a load on the surface. Now, in contrast to a finite element method, we don't split this into elements. We actually populate the domain with nodes. So here we've got 3x4 nodes, that's 12 nodes. And we connect every node to every other node, so that ends up being 11 times 12 over 2, which is 66 possible connections. And from that set of possible slip lines or connections, we use linear optimization to pick out the critical set of slip lines that form the collapse mechanism that dissipates the least energy. So in this case, there are 6 critical slip lines out of the original 66, and we get the mechanism shown in D. Now, we can extend that to use not just 12 nodes, but thousands of nodes and millions of potential slip lines and wedges, and that essentially is what LimitState GEO does. So it's taking well-known methods that are well established in textbooks, but just automating them and allowing you to extend them to thousands and thousands of sliding wedges. After the problem is solved, those slip lines can be connected up and deformed as solid blocks, and this animation is really here to aid interpretation, shows you that if collapse occurred, what it would look like. And a key point is that the number of nodes that we use in the problem will allow more potential slip lines, and there's a more precise mechanism to be identified. So in this animation you can see the nodes in the initial image just appearing now in the background. If you put more nodes in, then you get a more accurate solution. Obviously you want to be sure, confident that this actually does what it says it does. So every time the software is modified, we run thousands of tests to make sure it's churning out the same answers that we expect it to do. We put over 100 of these on the website, and essentially these have been calibrated against known solutions in the literature. So here we've got an example of an undrained passive retaining wall with full adhesion on the back of the wall. The benchmark is 3.07 from the literature. The result was 3.1 from the software, so that's less than 1% difference, and that's with very few nodes in the actual problem parameter space. And we've checked it against other well-known solutions. So here we're looking at the active earth pressure for a drained problem, frictional soil, and for a smooth and fully rough wall, and we get very good fit between the DLO results and the known theory, and the same for the passive case. Okay, so that's a little bit of background about the analysis method and the verification. Now I'm going to look at some examples, see how the software actually works. So if I just bring up the relevant file. Okay, so I've pre-prepared a gravity wall problem here. So this is the window of software. So typically we have a number of windows. The main center pane is the actual problem geometry. On the right we have what's called a property editor. Anything we click on in the main pane, its properties appear on the right. We can modify those. We'll talk about those a bit later. We have geometry editor. So the geometry of the object also appears here. Various buttons controlling the analysis top and to the side. We have what's called a materials explorer here. So these are all the materials that you can use in the problem. A number of predefined materials just for quick back-of-the-envelope type calculations, but you can define your own material properties. So for example, this soil A has a C' value of 0, Phi' of 38. We can also assign a CU to it and switch between the two, and unit weight, dry and saturated unit weight. And we can model linear variation of undrained strength if it's an undrained material. So that gives us the general layout, and we can analyze the stability of this wall. Now before I do that, just run through a few, we'll just flip back to the presentation and just say a little bit about gravity wall analysis. So in conventional terms, in sort of textbooks and codes, often it's recommended to check stability for sliding, overturning, bearing capacity, and also global failure, where the failure may sort of bypass the wall. However, this is really only a check of 3 failure modes out of an infinite number. Generally what happens is you get a combination of these rather than them individually. So the conventional approach is based on hand calculations. Those would be difficult to do for thousands of different mechanisms, and generally it's been found if you check those 3, generally you're covered. With the software, there's no need to carry out those separate checks. The software will find the critical mechanism, whether it's sliding, overturning, or bearing, or some combination of that sitting in between those methods. So it will always give you that critical one, so you don't need to do 3 or 4 separate checks. Now, before we look at how we actually do that analysis, we just need to say a little bit about ultimate limit state analysis. In general, when you're designing something, if you've got it right, it's going to be inherently stable and won't be anywhere near its ultimate limit state. So to do a kind of true ultimate limit state analysis, we have to drive the system to collapse by some means. And we can do this implicitly or explicitly. In many conventional analyses, the sort of thing you see in the textbooks, it's kind of implicit. It's not really stated specifically that this is what you're doing, but because you're analyzing it at the limit state, so for retaining walls, because we're assuming active and passive earth pressures, effectively we're assuming the system is collapsing. But to do this in a numerical approach, we have to do it explicitly. And there are 2 main ways to do this. It's what we call a factor load approach, which simply says if we have a load in the system, how much bigger does that have to be to cause collapse? Or by what factor does that need to be increased by to cause collapse? And that factor we call is the adequacy factor on load. And a load can be a surface load or can be a soil self-weight. So we could say how much heavier does the soil behind the wall have to be to cause collapse? The other approach is a factor strength approach, which is simply how much do we have to reduce the strength by to cause collapse? And that gives us an adequacy factor on strength. So we'll see how that's used in a moment, but general, if the adequacy factor is bigger than 1, then our system is stable because we've had to increase a load or reduce a strength to get to collapse. If it's less than 1, the system is unstable. And in general, if you're going to apply adequacy to a load, you should apply it to an unfavorable load in the system. And if you've already got partial factors applied, such as in a Eurocode approach, this adequacy factor will correspond to a global factor of safety or over-design factor over and above the measure of safety that you have from the partial factors. So, quick demonstration. So we'll go back to this gravity wall and have a quick look at the material. So as I said, this is retaining a soil, which if we click on here, we can display its angle of friction, 38 degrees, unit weight 18. Haven't got time to explain all the other parameters here, but that's the basic one. In the software, it is possible to separately define interface material, so the interface between the wall and the soil here has been defined for different material, and I've set an angle of friction of 25 degrees there. And I've said this material is always drained, so we'll always get a drained analysis. It's always going to use the effective stress parameters rather than the undrained parameters, but we can flip the different values if we wish. And we've got the same, we've got a soil here which is a little bit stronger on the base, a dense sand 45 degrees, and another interface material there. So if I do a factor load approach, what I'm doing is I'm just saying how much heavier does the soil behind the wall have to be to cause collapse. So I simply click the solve button and it quickly runs through and finds the most critical collapse mechanism for the nodal distribution that I've set up. And that's a sliding failure. Because it's actually employing rigorous principles of plasticity theory, the friction is represented by dilation. So the animation, you see some dilation going on here while it's sliding. And we get a very simple wedge mechanism. And we have an adequacy on load of 2.37. And if I click on that number, the software tells me what that actually means. It means that for object 2, which is that one there, click on that, we had specified a value of 18. If we had partial factors, this would be the design value, with the partial factors in this problem are unity, so that's 1. And that's what it would have to be to get collapse. That's a lot bigger. Alternatively, I can flip to factor strength and run the problem. And this time it identifies the mechanism. So what it's doing is looking for the critical mechanism where I don't have to factor the loads, but I have to reduce the strength of soil. So this is what I get. This time, because I've factored the strength, I can get a different looking mechanism. So this time what's actually happened is the wall is rotating slightly, still generally sliding. And if I click on that number there, it tells me that what I've had to do is factor all these material properties down to this value to get collapse. But either way, my adequacy factor is bigger than 1, and by either approach, if one value is bigger than 1, the other value is going to be bigger than 1, whether you're using factor strength or factor load mode. And if I click on this solid here, you can actually see it's displaying the normal stress distribution, so we're getting increasing stresses on the back from the earth pressures, and most of the stress is concentrated back here from the rotation. If I wanted to analyze this wall using Eurocode factors, I can do that. We have what's called a scenario manager, which allows us to apply partial factor sets. Currently they're all set at 1, but I can choose a different set. So I've got a pre-programmed Eurocode factor set, which essentially factors the strengths down by 1.25 for the effective stress parameters. So I click OK there, and I can run that solution again. And again, it's searching for the critical mechanism. And if I get a factor bigger than 1, then that means I comply with the code, and the magnitude of that number tells me how much bigger, what degree of over-design I've got in there. So in this case, it's going to come up with a value of around about 1.07, I think, 1.08. So that means it complies with Eurocode, and I've got an extra 8% margin on the strength of the soil before this thing will collapse. Just to wrap up that one, I'm going to flip back to the unit partial factors and factor load mode. So that's broadly, those have been sliding with a bit of rotation. If I put in a much weaker soil here, like a loose sand, so that's got properties of 30-degree friction angle, and do my analysis, then because I've got a weaker base soil, then I'm more likely to get more of a rotational failure. So there's a bit more rotation going on there. Still, it's a combination of sliding and rotation, which is what you're going to get. And in this case, you can see that the mechanism actually touches this base boundary. That's fine if there is, for example, rock or something very strong below that. If not, I should move the boundary downwards to make sure the analysis is correct. So that's a gravity wall approach. I can also analyze gabion wall problems. Now, gabion walls are pretty much like gravity walls, except the gabions themselves, you can get failure between the gabions. So for this model, I'm going to use a wizard. So the software comes with wizards which allow you to set up standard problems very quickly, but you're free to choose an empty project and draw your own geometry or import the geometry from, say, a DXF file. So you're fully flexible in how you change the geometry. So I'm going to pick a gabion wall here, and I can define various parameters here. So I'm going to set this height of 7 and a width here of 8, and I'm going to pick 6 gabions, and I'm going to accept all the other defaults. So I get a wall that looks like this. So we have a gabion wall, some fill between the wall and the main soil body, and it's founded on a different soil body. So these all have different properties. We could look at those, but in this short presentation we don't have time to go into all the detail. So the key thing about the gabions is actually what's going on in between them. So in between each gabion we have some materials. We have what's called gabion internal interface, so it's a more Coulomb material. So that's a frictional value. It's been set here at 35 degrees. So that means each gabion is able to slide relative to its neighbor with an angle of friction of 35 degrees. And we also have a cutoff material, and this has a limiting, if I just pull that back a bit, limiting compressive and tensile stresses. So what that means is if the stresses exceed that value, we can get failure. So if the compressive stresses exceed 500 kPa, we can get crushing effectively. So this allows the corners of the gabions to crush if we wish to model that. And by setting the tensile limit as 0, it allows them just to rotate as rigid bodies apart from each other. So we click solve and see what happens. Now in this case the whole gabion wall is remaining pretty coherent, and the failure is essentially it's acting as a gravity wall. There's a little bit of rotation of this top gabion like that, with the other ones coming underneath it. And we're getting inadequacy bigger than 1, so that means our system is essentially stable. Just to show that we can get failure along the interface, what I'm going to do is take this soil here. If I click on that, its properties appear here, and it's actually modeled as an undrained soil, as a clay, and I'm just going to set its strength very high to 500. So essentially that bottom gabion element is locked into this soil here. So if I then rerun the problem, we get a different mechanism, and you can see that the software then chooses to slide along the next interface up to get that failure. So hopefully you can see from that the software is free to choose where it's going to fail, and so it can identify any of the critical failure mechanisms for the gabion wall where we get failure along the interfaces. And we are free to change the geometry of this system in any way we like. So if you want to modify the profile of the soil, it's quite possible to do that just by clicking on parts of the geometry, moving those around. So I can Doesn't seem to want to do that for me at the moment. Yeah, I can move things around like that. Free to do any of that, and then when you click solve, it just solves that new problem. So if you want to modify the geometry or change material properties, it's very quickly to switch them in and out. Okay, so that's a look at gabion walls and gravity walls. So if we go back to the presentation, next example we'll look at cantilever and anchored sheet pile walls. So a classic cantilever wall type analysis, sheet pile wall analysis, involves assumptions of Rankine earth pressure distribution. So we assume, as I've said before, the wall is failing, the soil is failing around it, and that we have a point of rotation towards the base of the wall, such we get active and passive here, and they flip over below, and we look for horizontal and moment equilibrium in order to do our design and analysis. So typically we're interested in what length do we need for stability and what is the maximum bending moment that we're going to get in that wall. So we'll have a look at a model for that. Open that one. So here I've made a model of a cantilever sheet pile wall. So in this particular model, I've modeled the wall as a very thin block of essentially a rigid material with a unit weight of 24. So I'm actually representing a concrete wall in this case. And I can define interface elements between the soil and the wall. So that's my interface material. And in this case, I'm using what's called a derived material, which means that I'm saying the strength of that material is 1/2 of the parent material, and the parent material is this loose sand, which is an angle of friction of 30 degrees, and that parent material is what I've employed around the wall. So if I change the properties of the parent material, the interface material will automatically follow. I've got a surface load applied here, and that is essentially what I've got the adequacy factor applied to in a factor load mode. So if I click solve on here, I'll get a mechanism. The wall will rotate to the side, and if I click on the wall, you can see the pressure distribution, effectively active earth pressures down here. Right down near the bottom, we've got the point of rotation, so we flip the passive pressures here, and the same here, we've got passive pressures, and then we're flipping to active pressures, or not quite the same because that idealization in the textbook analysis is not quite what happens. But what we see is we've got an adequacy factor of 0.862, so if I click on that value, it says the surface load needs to be multiplied by that value to cause collapse. So basically, the system is currently overloaded. That surface load is too big, and the system is going to collapse unless we do something about that. So we need to make the wall a bit longer, and so I just happen to know that if I change that value to something slightly lower down, and it's only a tiny change because in this case we only need a very small change in that load, then I get an adequacy factor, not quite 1 but almost 1. And then the pressure diagram for that will correspond to an unfactored load at the surface. So that's a cantilever wall that gives me the earth pressures. If I want to model, but I can also model bending in the wall, but to do that I need to use what's called an engineered element. So here I've got a cantilever wall model, and this time I'm employing on that boundary what's called an engineered element here, and it represents a sheet pile. Now this engineered element is something in the software that allows you to model soil reinforcement, soil nails and sheet pile walls, and it depends how you set the parameters. Essentially, by setting this to be a very large number and that to be a very large number and these to 0, we're modeling a planar material. This is the bending moment strength of the material, the sheet pile wall. We can also model rupture, tensile and compressive failure. But for a sheet pile wall, really we want it to be to model bending strength. And these parameters generally used for soil nails, so we don't need to worry about them. Again, I can just solve this problem as a factor load problem. And what we get here is an adequacy factor of 1.4, so it's basically telling me that in order to get this thing to collapse, I have to multiply the weight of this block of soil behind the wall by 1.4, so it's got to go from 15 to 20, and then the system will collapse. It's showing me the mechanism, and it's showing me the bending moment distribution. So if I hover above these points, I can see what the bending moment. But you have to remember that that bending moment distribution corresponds to the problem where the weight of this block of soil has been increased by a factor of 1.4. So that's in that particular scenario, which is not the actual scenario where, because this weight would not have been increased. If you want the actual bending moment, we really need to design the wall to be at its optimum length. And I just happen to know that that's around about 2.1 on this value. So if I shorten the wall, because at the moment our adequacy factor is bigger than 1, the wall is too long, and then rerun the analysis, I get an adequacy factor very close to 1. And so now, effectively, we haven't had to increase the weight of this block of soil. The wall is just on the point of failure, and these are the bending moments in the wall, and they're analogous to those that you get from a conventional calculation on this problem using the sort of textbook approach. But the software is able to model bending in the wall, so at the moment the strength of the wall is much higher than the actual predicted bending moment. If I just reduce it by, say, a factor of 10 and run solve, what you can see is that the software said, well, you can bend here. The bending moment's actually reached 15 at this point, so we can get a failure mode, and we have a very low adequacy factor. And essentially it's saying, well, because of this much weaker wall, you'd have to reduce the weight of the soil behind the wall down to a unit weight of 5 just for it to be at the point of failure, because we weaken this wall. But clearly that's not what we want to do. We'd want to have a stronger sheet pile wall and get that bending failure. So that's cantilever wall analysis, and if I just jump back to the PowerPoint. Just useful just to recap on what I've just said there. If we have an adequacy factor and load bigger than 1, for example, on the soil behind the wall, so that means our wall is over-designed, then any derived bending moments, pressure distributions we get relate to that problem, analysed with that non-unit adequacy factor applied. So we generally get bigger moments than we'd want. So that means any values we use there are going to be over-conservative. And when you do a conventional textbook calculation, typically you're designing the wall to be of the right length so that everything's in equilibrium without having to factor up the weight behind the wall, so all the values are exactly as you want. If for any reason you have to analyze a wall that is over-designed, and there are many reasons why that might happen, then though obviously those bending moments are not going to be the ones that you want to use. So there are various ways around this. One is simply to reduce the wall length to give you an adequacy factor of 1. So you calculate the bending moments for that. You know the wall will work for that. If you make the wall longer, it's going to be stronger. The system's going to be stronger. It should cope with that fine. You can also, taking the full power of the software, is reduce the bending strength of the wall, as I illustrated, till we get a bending failure and the adequacy factor comes down to 1. And then that gives you actually an indication of the bending strength required to avoid an ultimate limit state. Or finally, we could actually do a factor strength calculation. That doesn't change the factor on the loads, but the results we get will be similar to a mobilized strength approach. So typically when you're using mobilized strengths, we're getting more towards a sort of serviceability limit state type analysis, and we're typically going to get higher bending moments. But I think the first two are the better approaches in this case. Okay, we're coming towards the end of the presentation, so I'm just going to wrap up with a little look at anchored wall analysis. So here we have an anchored sheet pile wall. We've got an anchor tendon here and a deadman anchor at the back here. Typical things we're interested in are modeling those aspects. What is the load in the tendon, and how does that wall interact with the deadman? So in classical design, the ideal spacing, or the minimum spacing, is such that the mechanism in front of the deadman just touches the mechanism behind the wall. So that's what I've got set up in this particular animation. So we'll have a quick look at that problem in the software. If I can find it, yep, there it is. So that's the problem set up. I'm going to solve that. So we set it up as a factor load problem, so we're increasing the weight of the soil behind the wall to see what causes collapse. We could have set it up as a factor strength problem. And in this case, we've got an adequacy factor of 0.962, so it's almost ideally designed, and you can see here we've got partial factors applied from the Eurocode, so that means we've already got a margin of safety built in. The way the model is built is the wall is constructed using again an engineered element, which is a sheet pile wall with a bending resistance of 500, and either side of it, on the right and on the left, there's an interface material which defines an angle of friction. So that's the wall-soil interface friction angle, and in this case I defined it as 22.66 degrees, which should be 2/3 of the angle of friction in the soil. In fact, it's slightly bigger than that in that case. The anchor tendon is also constructed from an engineered element, and any engineered element that contacts another element transmits its forces to that element correctly. Now here we've essentially set factors here all 0, and that basically means that the tendon does not interact with the soil that it passes through. It's just able to transmit a tensile or compressive force, but in no other way it interacts with the soil. We set a moment of resistance there of 0, so that means it can bend freely and that it will fail in tension at a strength of 250 kilonewtons per meter in the diagram. Now there's a subtle detail in the connection that we're actually connecting the tendon to the wall by a little extension element, and the reason we do that is because we model the tendon as having no bending strength. If we were to connect it directly to the wall at this point here, the software picks the lowest strengths of all the elements that are connected to it, and so it would just model a hinge in the wall. So we add a little extension here, and that stops us modeling a hinge in the wall. And it's what we've done on the other side here as well, little connector to this deadman anchor, and the deadman anchor is basically modeled exactly the same as the wall itself. So that's how we've set up the particular model, and shown how the initial analysis has no interaction. And what I want to do in this particular problem is actually to show the interaction between the anchor and the wall. So I'm going to select the 3 elements of the anchor. I'm going to click a button here called Ortho. What that means is if I try and drag any elements on the screen, they'll only drag vertically or horizontally. And I'm going to move this a little bit closer to the wall. And I'll rerun the solution. And this time the wall and the anchor are not really behaving separately. What's happening is that there's kind of a block of soil between the two, and it's behaving like a sort of large monolithic block of soil sandwiched between these two walls. We get a lower adequacy factor. That means this is definitely unstable now, and a different mechanism, which is more like sliding the rotation of the main wall body. And if I move that a little bit closer, then the anchor is clearly going to be interacting more and more, behaving as part of the wall, and our adequacy factor drops even more. We've still got a bit of a wedge of soil in between there, but in the extreme I can push this right up. So what I'm trying to illustrate here is that we will get the full interaction of the two systems, and you'll get the corresponding analysis in that case. So here effectively we're almost back to just a simple cantilever wall analysis and a very low factor of safety in this particular case. So we can deal with interaction of those components. Okay, so we're just coming up to wrapping up the presentation. So come up with some conclusions. So hopefully I've shown you that retaining wall analysis and LimitStateGEO uses similar principles and mechanics as conventional limit equilibrium methods, but we can handle complex geometries and kinematics and obtain very accurate solutions. There's no need to separately consider different failure modes, as in classical approaches, such as sliding or toppling. They're all automatically dealt with, and the most critical one found, even if it's a combination of some of the classical ones. And it automatically searches all these possible failure modes. With respect to retaining walls, it's quite easy to handle variable surface loads with different positions. We can handle variable backfill geometry, including slopes behind the wall. Didn't actually illustrate this, but we can use the software to model tension cracks in the soil that form between the soil and the wall if we've got cohesion in the soil. We can model the wall interface, soil interface friction different to the soil itself. It's very easy to model layered soils. Again, I didn't really touch on that, but putting in layered soils is very straightforward. The software deals with that. And we can add water. Again, I didn't have time to talk about water, but we can add water tables into the problem and model those. So hopefully, having seen how the software is used, you've seen how interactive it is and how quickly it solves. So a lot of people use it just to answer what-if type questions. Gives you a much better feel for the problem before you actually go and design the solution, and that the one piece of software can solve any ultimate limit state problem type. So there's no need to bring in idealizations or correction factors for non-standard geometries, and no need to learn how to use many different programs. So that's the end of the webinar. We move on. We've got a few minutes left to answer any questions. So if you've put any questions up, they should appear. I can find them on the system. It'll take me just a couple of seconds to pull that up. Okay, so I've got a question asking what type of connections, material properties did I use for the anchor plate connections. So if I just bring up that anchor wall problem, I'm just going to click undo here. So anything I've done I can just undo and revert back to where I was before. So I think the question would be, what kind of material did I use there? And essentially I just used the same material as the anchor itself. So I just are using a material that behaves as a planar sheet, which is essentially those parameters there. More detail is given in the manual. And anything that's on here that you click on, there's a brief description appears in this little window down here, and you can click on a link that takes you to the manual. But effectively it's modeled as a sheet with a high bending resistance. So effectively that little short connection is just modeled the same as those. I haven't bothered modeling the interface materials on that because it's such a short section, but you could do. But in this case I've only modeled it as 0.1 meters long. It doesn't really matter how long you do it as long as it's small, and just make sure that this point here is different to that point there. Another question, virtual back. Let me just open up that. So this is a wizard that's drawn the a cantilever stem wall. Now, in classic analysis on that, one might have a virtual back on the wall in order to work out pressure. The software doesn't put in virtual backs. It doesn't know what it's modeling. It's just modeling a set of materials and certain geometries. So if I solve this particular problem, what it does is finds a mechanism it's essentially crossing what would be a virtual back in classical analysis, but it's not really going into this triangle, which is as you'd expect. This is fairly confined, so there's not really going to be any deformation in that. So it doesn't model a virtual back, but it does find the critical mechanism there, and you get very similar answers to if you modeled a virtual back, but the virtual back does bring in a bit of an idealization. I've got a question: have I followed the Carousel and Absci method to find the pressure coefficients for Eurocode 7 calculations? That might refer back to the PowerPoint. Let me go up to these graphs. Yeah, these graphs here. So again, the software doesn't know that it's solving a retaining wall problem. All it knows is it's solving a collapse problem, and it's finding the optimal mechanism for collapse. And these graphs here are just saying basically the optimal mechanism that it's found coincides exactly with the known solution for the active or passive pressures on the wall that have been found by researchers such as Carousel and so on, and are quoted in the Eurocode. So the software doesn't have tables of these coefficients written into it. It has no idea. It has no bearing capacity coefficients, no lateral earth pressure coefficients built into it. It's just finding the critical collapse mechanism, and we're just showing here that when it finds the critical collapse mechanism, as it should, it's finding the coefficients that have been defined in the classical literature. I think at this stage there's quite a lot of questions come in, but we are out of time. So what I will do is we'll make sure that we do reply to all your questions by email, but apologies that I haven't had a chance to do that at this particular point. But what I'll do is hand back to my colleague Tom just to wrap up. So thank you very much for listening, and I hope you found that useful.
Thanks, Colin, and thanks to everybody for listening today. So, as Colin mentioned, we're now near the end of the webinar, and we do hope you found it informative and useful. As I mentioned at the start, if it's prompted any questions that are outside of the ones that have been posted today, then please do get in touch via telephone, or if you email support@limitstate.com, we'll be happy to answer any questions that you might have. For people who aren't actually current users of LimitState GEO, we'll just get in touch over the next few days to get some feedback on the webinar and find out if you have any further questions, or if you think LimitState GEO might be useful for you. If you would also like to watch the webinar again, or if you think you might know somebody, maybe a colleague who'd be interested to see it, then what we'll do is we'll make a recording available for you later today or early tomorrow, and we'll send out an email link once it's available online. Lastly, please do look out for our other webinars that deal with LimitState GEO. We send out event notifications via email in advance of these, and they will also be posted on our website at www.limitstate.com/webinars, so you can keep an eye out for them there. So finally, I'd just like to say thank you again for listening, and we do hope you can join us again for one of our future sessions. Goodbye.